Now we're going to turn our attention to the respiratory system. And in particular, we're going to begin with what occurs within the lungs, the gas exchange between the air that you inspire and the blood that flows through the lungs. Now, the respiratory system exists so that we can bring oxygen into the blood and offload CO2. There's also the ability to control pH. We'll get into that in a little bit. Why do we need to do this? Well, because all of the cells of the body require oxygen to undergo aerobic metabolism, which provides a very high yield of ATP in the cells for each molecule of glucose or fatty acid that makes it inside the cell. And a byproduct is CO2. Okay, so we have the lungs and all the vascularization within the lungs because of that, because the cells need oxygen. So the first question that we're going to address is, how can gas exchange be maximized? So we're going to consider the physical principles of exchange. We're going to consider the role that blood chemistry plays in this, and in particular the solubility of oxygen in the blood, and then finally the transport of carbon dioxide. So on each of these subjects, we're going to pose the question, how do we get the most? How do we get the best exchange? And you can think of this in the context of activity or even intense exercise, that the respiratory system and the circulatory system in its delivery of oxygen provide limiting factors to activity. If you have insufficient ventilation in the lungs or insufficient circulation, then you will feel fatigued and you cannot meet the aerobic demands of cells, especially exercising cells, the skeletal muscles. All right, so let's start with the physical principles, and we're going to consider the physics of gases first. And what we've got here is a beaker, and this is going to provide us with a greatly simplified model for what occurs within the lungs. So you breathe in, that ventilates very small containers called alveoli, we'll talk about those later, that hold the air in close proximity to capillaries that carry the blood through the lungs. So in this model, the gas mixture above this interface, which is just a volume of water, serves as a model for the air inside of the lungs, compared to a liquid, which is our model initially for the blood that flows through the capillaries. So the air pressure itself, even at elevation, air pressure, which is generated by the collisions of gas molecules against surfaces. After all, these gas molecules have mass, and they move around with random thermal motion, but that motion sometimes causes them to collide with surfaces like the wall of this beaker or the surface of the water. And they'll either bounce off, say, a solid surface and impart some momentum to that surface. That's what generates pressure. Or sometimes they'll actually penetrate a liquid surface. So you could say that air pressure is driving, in this case, oxygen. So we've labeled the molecules here that correspond to oxygen. The most popular gas in the atmosphere is nitrogen. So you can imagine most of these gray dots are nitrogen molecules. So we have some oxygen penetrating the surface and diffusing into solution. Now, here's where the ideal gas law comes into play. The ideal gas law is a model of the relationship between pressure and other aspects of a gas that's in a container. So we have the volume of the gas within the container. You have the number of molecules in terms of moles of that gas that's within the container. Then there's a couple of constants. So you have the gas constant and then temperature, which can change, but in the body it stays pretty consistent. So what the ideal gas law lets us do is consider what factors influence the pressure. Since we've established on the left that pressure is driving the oxygen into solution, if we can change the pressure of the gas mixture above the interface, then we should be able to manipulate how much oxygen we drive into solution. So if we take the ideal gas law and rearrange its terms, we can see that we can come up with an equation for pressure, and we can see that if we want to maximize the pressure, again, how to get the most exchange, then we can elevate that pressure of the gas by, in one sense, reducing the volume of the gas mixture above the interface. So we do this virtually here by adding a plunger to our system, and just imagine comparing the beaker on the left, which is open, to one where we have a closed volume, and we're going to make that volume smaller. So that's going to serve to elevate the pressure, which is going to drive more oxygen into solution and give us a higher concentration of oxygen molecules. Now we can go back to the initial form of the ideal gas law to see that the product of pressure times volume is equal to all the other stuff in the equation. So what is that? Well, it's the number of gas molecules, some gas constant, something that's not going to change, and the temperature, which for our current purposes doesn't change either. So in other words, the product of pressure and volume is fixed, provided all the other stuff stays the same. And that relationship is important when we think about what occurs within the lungs. And it was initially formulated by Boyle. And so we have this left-hand side of the ideal gas law, PV, included in what's called Boyle's law. So Boyle's law says that basically PV is going to stay the same. So if we look at the PV on the left, we could just imagine there's a sort of virtual ceiling to this volume, because that's where the plunger began before it moved downwards. So that volume times the pressure is going to be equal to the same product on the right-hand side. And since we have reduced the volume, that means we've increased the pressure. Okay, so this is formalizing something that I think makes intuitive sense, which is we've got a fixed number of gas molecules. Each gas molecule contributes to pressure. And when you reduce the amount of space that those little masses have to bounce around, then you're going to increase the frequency that they encounter those surfaces, and that's going to impart more momentum, which is going to be reflected in the pressure. Okay, so we're making basically a tighter space for these little bouncing balls of these little gas molecules, and if you reduce the amount of space that they have to move around, you're going to elevate the pressure. Okay, another trick for enhancing exchange would be to manipulate something else in the equation, and in particular, if we change the number of gas molecules, so the moles of gas, and rather than changing the total number, which would affect things, but quite often, the atmospheric pressure is beyond our physiological control. It's just dependent on our current elevation. So we're if you're at sea level, then that's one atmosphere of pressure that you can't really do much about. But just imagine that instead of changing the total number, what if you were to swap out some of those nitrogen molecules for oxygen molecules? Again, not really physiologically possible, but we're just playing a thought experiment here. And so we do that on the right-hand side. So even though the total pressure would be the same in both of these beakers, because we've swapped out or we've enhanced the proportion of those gas molecules that are oxygen, then you would expect a higher concentration on the right beaker than on the left beaker because of that swapping of the molecules. And this illustrates something known as a partial pressure, which is formalized by Dalton's law. So Dalton's law it's pretty simple. So it's basically that the idea is that the total pressure, air pressure this is generated by all of the gas molecules bumping into things. And so the proportion that is due to any particular kind of gas, like oxygen, is just quite simply the proportion in numbers of the gas mixture that is composed of that type of gas. So the partial pressure is essentially the proportion of pressure, so that's either pascals or millimeters of mercury, that is generated by one type of gas. So here we have the partial pressure for O2, that's oxygen, is the product of the total pressure, so that would be like 1 atmosphere at sea level times the percent of oxygen that's in the air. So on Earth, that's 21%. Now you can calculate a partial pressure for any gas. It could be nitrogen, it could be carbon dioxide. And we could apply Dalton's law. Just take the total pressure, multiply it by the proportion of the total of the gas mixture that is composed of that particular type of gas. So we can do that calculation. So in the air, we have for oxygen, they're 21%. Carbon dioxide is tiny. Okay, we have 0.033% of the air that we breathe is composed of carbon dioxide. Now, if we multiply those proportions into the atmospheric pressure at sea level, then we can find the partial pressures of the two. And so because of that really high percentage, and we're multiplying those percentages by the same number, then not surprisingly, you get a really big number for oxygen. You would say that the partial pressure for oxygen, shown in red, favors diffusion into the blood. Because you can think of the partial pressure as being a driving force. Okay, what we saw in the last example of the beakers was that in those two cases, the total pressure was the same, but because on the beaker on the right, we had a higher proportion of O2, that meant that the beaker on the right had a higher partial pressure than the one on the left. So it's really partial pressure that matters as a driving force for diffusing a particular gas into solution. So the partial pressure for O2 is much, much higher than CO2. And it's really the partial pressure difference between what's in the air and what's in solution. So, given that carbon dioxide is a very small, offers a very small partial pressure, that's going to favor the diffusion of CO2 leaving the blood in the lungs, whereas that very high partial pressure for O2 provides a driving force for diffusion into the blood. So we can say that the gas composition of air favors the exchange that we want. We want as much oxygen into the blood as possible and as much CO2 to leave. Now, that brings us to the other side of this equation. Okay, so air favors what we want, that is, this exchange of O2 and CO2. But on the receiving end, we've got a problem. And that brings us to blood chemistry. So let's consider an example. So this is unrealistic, as I just laid out, in that the partial pressures for O2 and CO2 are equivalent. And we're doing this unrealistic scenario in order to illustrate what happens on the receiving end. That is the solubility of these two gases. So we're offering the same driving force to provide a controlled virtual experiment. So if we have both 100 millimeters of mercury for CO2 and O2, and we measure the concentration of these gases in solution, then what we find is that the concentration for O2 is something on the order of 0.15 millimolar per liter. Okay, that number by itself doesn't really mean very much, but if we compare it to CO2, we can see that many more CO2 molecules dissolve into solution. In fact, that difference is 20-fold. Carbon dioxide's 20 times more soluble in water than oxygen is. Okay, that's a problem. If the goal is to bring oxygen into the system, into the liquid, and we want to get rid of CO2, we can see that water provides a challenge because water is really greedy. It wants to hold on to CO2 and it doesn't really take on much carbon dioxide. Now we might ask the question, is water a reasonable model for blood? Blood's got proteins, you've got red blood cells, all kinds of stuff. Is water a reasonable approximation? And one thing we can do, and physiologists love to do this, is to provide a sort of back of the envelope calculation just to see whether or not we're in the right ballpark. Like, is this a reasonable model or not? Or are we missing something in our model for blood here? Well, if we convert this concentration of oxygen into milliliters of O2, which is another convention in physiology, we've got milliliters of we've got 0.8 milliliters of O2 in solution. This is for water at atmospheric pressure, 21%. Or actually, I should say, sorry. So this does correspond to atmospheric pressure, not necessarily the pressures that are shown up above. So this is the concentration that we get, because what we want to consider is whether or not at sea level water would be sufficient to transport oxygen. Okay, so let's actually replace water with plasma. So plasma doesn't include red blood cells. It's just all the proteins and the other chemistry that's in the blood. And we're doing this to see if plasma provides a sort of enhancement in the solubility of oxygen in the blood. And by the way, this should be milliliters of O2 per liter of water. So that slash should have an L to the right of it. In plasma, we find that actually, yeah, the solubility is quite a bit better. It's not as good as what we see for carbon dioxide, but it's more than 3 times better than water. Okay, so there's something about those proteins and the other stuff that's mixed in the plasma that really helps. All right, so now we can pose the question, is this enough? Is the solubility of plasma enough to meet the metabolic demands of the body? All right, so here's where we get to our back of the envelope calculation. We know from respirometry measurements that a body at rest needs 250 milliliters of O2 per minute. Okay, so that makes sense because it's a quantity of oxygen per unit time. It's not per liter because it's for the total body. There's no particular volume that we're concerned with. We just want to know what's the total amount of oxygen that we need per unit time. So we've got a quantity here, which is a concentration, so how much oxygen per liter. And we want to get something that's oxygen per unit time. So we want to multiply this by something. What makes sense? Let's see. So units-wise, it should be liters per minute. So what's liters per minute? Oh, okay, I know. The flow rate, that is how much blood is circulating through the circulatory system. Okay, so we take our concentration of oxygen per liter, provided this is what's provided by the plasma. We multiply it by the flow rate. We can look that up. So that's our liters per minute. The product is 15 milliliters of O2 per minute. In other words, 6% of the metabolic demand. All right, so plasma does not provide sufficient oxygen delivery to the aerobic cells of the body. All right, so the big missing ingredient here are the red blood cells. Let's consider the chemistry of that. So we're going to add to the plasma those red blood cells, which are known as erythrocytes. So we zoom in here. This is what erythrocytes look like. They don't have a nucleus, and they are just packed with a really important molecule for this transport problem, and that's known as hemoglobin. Hemoglobin includes iron in each of what are called heme groups. The heme groups are really good at binding to oxygen. So you can think of the red blood cells in this context as packages of hemoglobin, each of which have 4 binding sites for 4 oxygen molecules. And it's just packed with thousands upon thousands, and the circulatory system is packed with the red blood cells. So this is really the difference, okay? This is the difference between the sort of paltry performance of oxygen transport provided by the plasma and what the blood is actually capable of. And the dynamics of hemoglobin turned out to be really important and also flexible. They change under different physiological conditions through blood chemistry. So let's consider that. And we're going to do that by just considering blood in a dish. So here we have a petri dish, and we're going to fill it with blood. And we're going to monitor how much oxygen is in solution. And we're going to place our petri dish in a chamber that allows us to manipulate either the gas mixture or the total pressure of the gas that comes in contact with the surface of the blood. Now, this is important to bear in mind the origin of the measurements that I'm about to present, because we're going to make inferences about what happens in the lungs and what happens at the cells, the exchange of gases at the cells. All of this is inferred from a relatively simple experiment. Okay, so just bear that in mind, the nature of sort of the source of the measurements compared to what we're inferring. It'll become a little bit clearer in a moment. So here we have our measurements. The x-axis is what we're controlling, okay, the partial pressure for O2. Now we now know from Dalton's law there's 2 ways you could do that. You could vary the total pressure and keep the proportion of oxygen at 21%, or you could keep total pressure the same, but you could infuse a higher concentration of oxygen to boost its partial pressure. You get the same result either way. And then we're going to use our oxygen electrode to get the total saturation. So if the oxygen electrode measures in terms of milliliters of O2 per liter of blood, or maybe moles of O2 per unit volume, something like that, then that gets normalized by the maximum, you know, the highest concentration of oxygen that we can get in the blood. And the way that this curve looks, and it's largely driven by hemoglobin. If you remove hemoglobin from the blood and you just do this experimental plasma, you don't get anywhere close to the same levels of saturation. So really, hemoglobin is where it's at. That is the molecule that matters for oxygen transport. So we go from a partial pressure of 40 millimeters of mercury to 100 millimeters of mercury. 100 millimeters of mercury, it turns out, is the partial pressure encountered in the lungs. That is, the gas mixture in the lungs achieves something close to 100 millimeters of mercury. So in this experiment, that's what we're manipulating. It's the gas above this interface with the blood, and that's simulating at 100 millimeters of mercury what the blood is exposed to in the capillaries in the lungs given the air that's inspired in the lungs. The blood then gets transported through the body. It eventually finds its way into capillaries that provide vascularization for the cells that need it. Cells of the body commonly have a partial pressure of 40 millimeters of mercury. So blood is going to be moving up and down this curve, okay? So initially, when it becomes oxygenated, it reaches equilibrium with the air in the lungs. So it'll be at this level, and then the blood eventually finds its way to the cells, and it will move down this curve as diffusion drives oxygen from the blood to the cells that need it. Now, the shape of the curve matters to that transport. The shape in this part of the curve has a very slight slope, and we'll see that compared to the other part of the curve in a moment. But what a slight slope or a low slope on this curve means is that you need a really large increase in the partial pressure for O2 to go from this point on the curve, that is 75% of saturated, all the way up to 100% saturated. You have to traverse from 40 to 100 millimeters of mercury in order to get that last 25% of saturation. Now, even though I just told you that the cells commonly have partial pressure of 40 millimeters of mercury, it is possible when you're really active for the cells to achieve a much lower partial pressure, much less than 40 millimeters of mercury. This would especially be common under intense exercise. And we see that below 40 millimeters of mercury, a very different slope. Here, the slope is quite high, and what that means is that a small decrease in partial pressure causes a really precipitous drop in saturation. So we're going from 40 millimeters of mercury, I don't know what that is, like 10 millimeters of mercury. So that 30 millimeters of mercury difference is much less than the 60 millimeters of mercury that we see between 40 and 100. It's half. And despite that being a pretty small difference in partial pressure, we get this huge drop in the oxygen saturation. So on that part of the curve, just a really small decrease in partial pressure effectively releases a lot of oxygen, because the y-axis tells us how much oxygen is in the blood. If it's not in the blood, then it's released by the blood or in the air in the case of what's going on in the lungs. So when the blood goes from 40 millimeters of mercury down to this level, it's giving up that oxygen and making it available to the cells that need it. So when the blood encounters an environment that is a very low partial pressure, something like 10 millimeters of mercury, then it's going to liberate oxygen and make it available to the cells. Now, this relationship is known as the oxygen dissociation curve. The partial pressure for O2 increases in the plasma, and that causes hemoglobin to bind O2. All right, that's just a statement about the nature of the measurement that we're making here, that we're increasing the partial pressure in the plasma because we're exposing that plasma to an increase in partial pressure of the gas that's above it. Now, let's get back to the shape of the curve affecting this exchange. So just consider the exchange that occurs at the level of the cells. It's not hard to envision what happens in the lungs, right? We just basically, if the blood, when it returns to the lungs, is a very low partial pressure, then the capillaries in the lungs and their interface with the dissolved gas allows it to resaturate back to 100 millimeters of mercury. And then, as it goes back to the exercising cells, then the blood moves back down this curve. Okay, so that brings us to what's happening on the left. Now, initially, the cells encountered by this parcel of blood are at 40 millimeters of mercury. All right, so that's right here where we said the cells are at that level. All right, so that's going to cause the blood to drop to a saturation of 75. So going from 100 in the lungs, then it's dropping to 75%. That means it's making oxygen available to the cell. So when we look on the left, that's what we see. Oxygen is liberated. If it's not being held on to by the blood, that means it's being made available to the cells. And so as the red blood cells move through, then it's oxygen for everybody. All right, now our red blood cell and all the hemoglobin inside of it, all of the bound oxygen encounters some cells that are at a lower partial pressure. All right, 20 millimeters of mercury. Now, because we're on the part of the curve with the steep slope, that means there's a larger drop in saturation. That means that more oxygen is made available to those cells that are exercising most intensely. So this is why the shape of the curve matters. If this were a linear relationship, then any given drop in partial pressure would have the same amount of oxygen released by the blood. Instead, this nonlinear relationship means that you get more oxygen liberated for a given drop in partial pressure. Here we see a drop between 40 and 20. All right, so 20 would be like right in here. And we see a big drop, something below 50% from 75. Whereas a 20 millimeter of mercury drop on this part of the curve would just cause a change from like 100 to 90 something percent. Now, another key point for the oxygen dissociation curve is that the shape of that curve also depends on other factors that change under healthy physiological conditions. For example, pH. All right, the pH drops when you exercise intensely. We'll get to why that is the case in a moment. But what we see here is that we have a drop in pH. That means the green curve is a blood that is more acidic than the red curve. Let's just consider what happens at 40 millimeters of mercury. So we have, this is sort of typical for resting cells. We're at a lower saturation level on the green curve than on the red curve. So what that means is that the blood at a pH of 7.2 is going to be less saturated at 40 millimeters of mercury than the blood at 7.4. If it is less saturated, that means that more oxygen has been released by the blood, thereby making more oxygen available to the cells. And that's what occurs when you're very active. Your blood pH will drop. That will make the oxygen more readily available to those exercising skeletal muscle cells. And this is true at all partial pressures. You can see that the values of the green curve is less than the values of the red curve at every partial pressure. So we can say that blood is less saturated at lower pH. You get the same effect if there's an elevation in the partial pressure for carbon dioxide. So you get that same kind of effect. If the partial pressure for CO2 is greater in the blood, then the blood will be less saturated for O2. This matters at the level of the cells. You also get the same kind of effect if the blood is at higher temperature. Again, something that occurs in parts of the body that are exercising at high intensity. All of these are driven by an elevation in activity, and all result in the blood being less saturated with oxygen. Okay, so this all matters for the exchange that occurs at the level of the cells, not so much for the exchange that occurs in the lungs. Okay, the partial pressure of CO2 in the lungs is set by its exposure to the air that's inside of the lungs. That also causes the pH to not be acidic, and the temperature of the lungs should not be elevated, even though it might be sort of warmed up a little bit by the blood, but there is no elevated metabolism in the lungs like you see in the exercising skeletal muscle. So all of these effects really matter for the exchange that occurs with the cells. Another point here is that you see a very large separation between these curves at a partial pressure that you would expect for the cells, whereas at the lungs that are at 100 millimeters of mercury, there's really very little difference between those two curves. Okay, so this point about the effects of pH, CO2, and temperature really apply to the exchange that occurs in the cells. And what it favors is the release of more oxygen when you are more active. Okay, so everything I've described so far applies to the transport of oxygen to the cells. But of course, exercising cells and even resting cells that are using aerobic metabolism produce CO2. So how is CO2 transported? We see that hemoglobin is really, really important for O2, and it really dominates O2 transport. What about CO2? Well, let's consider the exchange of the cells on the left and the exchange of the lungs on the right, just to consider what happens to CO2 that's in the blood. Now, CO2 has some, like oxygen, low-level capacity to just diffuse into plasma and be transported in the plasma itself. That only accounts to 7% of the transport. Now, when red blood cells encounter cells that need oxygen and it releases oxygen, then hemoglobin itself can bind CO2. And that accounts for almost a quarter of CO2 transport is binding to the hemoglobin in the red blood cells. So we think of red blood cells as being oxygen transporters. They also, it turns out, transport a fair amount of CO2. Now, another thing that occurs in the red blood cells is the conversion of CO2 into bicarbonate. And this is the most popular means of transporting carbon dioxide. What does that conversion look like? Well, now I've mentioned pH a couple of times. This is the reason why blood pH changes, and it also provides the means for the lungs to influence blood pH. Now, excuse me, carbon dioxide in water in solution produces carbonic acid. So if you have a higher and higher concentration of CO2, then you just produce more and more carbonic acid. That in turn is converted into bicarbonate and a proton. And it's that proton that lowers blood pH. So effectively, in the exercising cells, when there's an elevation in carbon dioxide, that results in more carbon dioxide in solution. We go through this reaction that produces a high concentration of protons and also bicarbonate, and that serves to lower the blood pH. The blood pH is lower in exercising cells than what you see in the exchange that occurs in the lungs. Because in the lungs, you essentially have a reversal. The bicarbonate that is transporting CO2 is converted back to carbon dioxide and water. And this just occurs naturally as there's a reduction in the partial pressure for CO2 as it is exposed to the air in the lungs. Then there's a reversal of this reaction. And so blood pH will rise at the lungs because we're taking those protons, and in combination with bicarbonate, we produce water and CO2. The CO2 then diffuses into the lungs. So, in summary, we had this question of how can gas exchange be maximized? And we saw a variety of physical principles. There's the ideal gas law, which indicates that if you reduce the volume for a fixed number of gas molecules, or you change the number of gas molecules, then you can elevate exchange. That's then basically Boyle's law is the product of the pressure and the volume remaining the same as you change the volume. It's essentially an application of the ideal gas law. And Dalton's law articulates the partial pressure. So if the partial pressure is greater, then you have more of a driving force of a gas like oxygen into solution. Now, on the receiving end, blood chemistry really matters because it affects the solubility of O2 in solution. So you get the driving force provided by partial pressure, but then the amount that moves into solution depends on the solubility. So hemoglobin is really dominant for O2, and that's reflected by the oxygen dissociation curves, which also vary with blood chemistry, pH, temperature, and partial pressure for CO2. And then finally, we have carbon dioxide transport through multiple means, 70% of which comes from bicarbonate. Now, the big picture here is that this exchange works really well, and I should say the lungs work really well. If you look at the partial pressures in solution. Now, partial pressures, as I've mentioned, the quantity has to do with what occurs in gases, but it's a convention in physiology to talk about the concentrations of the gases in solution in terms of partial pressure. So in the blood, you can have a partial pressure. This is not actually a pressure that's generated in the blood, all right? That has more to do with all of what we said about partial pressure, systolic, diastolic, all the stuff for the left ventricle, the elasticity of the major arteries, all that kind of stuff is the actual measured pressure. But when blood is exposed to a gas of 100 millimeters of mercury, then it will adopt a certain number of moles in solution, a certain concentration. Okay, so this is somewhat non-intuitive because we're using the term pressure here for what occurs in a liquid, but it's not actually mechanical pressure. It's just the concentration that corresponds to what you generate from this partial pressure. Anyway, it's a long-winded answer to say that the partial pressure in the blood, it reflects a concentration of a dissolved gas. So the blood that leaves the lungs, that's through the pulmonary vein, has a partial pressure for oxygen of 100 millimeters of mercury, CO2 40 millimeters of mercury. And that's exactly what gets transported to the cells. The fact that it moves through the left heart doesn't matter. The cells have about 40 millimeters of mercury for O2, a higher value of 46 millimeters for mercury of CO2. Then the cells reach equilibrium with the blood so that the blood leaving the cells has the same partial pressures, that is, in the systemic veins. The blood then moves through the right heart onto the pulmonary artery. You see exactly the same levels there, okay? Then what the lungs do is essentially go from 40 millimeters of mercury for O2 to 100, and then we see an offloading of CO2 so that it goes from 46 to 40. And what I want to emphasize here is the nature of the exchange, okay? These are the values of partial pressures for the air that's inspired into the lungs, or I should say the gas mixture, by the time it makes it into the lungs, has 100 millimeters of mercury for O2 and 40 millimeters of mercury for CO2. So what the lungs do is essentially just get the blood in close proximity to the gas mixture so that the partial pressure in the blood matches that gas mixture. It matches what's in the air. Same thing for the cells. We see that the partial pressure for blood in the veins ends up equaling exactly what's in the cells. The capillaries just get the blood really close to the cells and they reach equilibrium. Okay, so our transport of dissolved gases is not done in a way where we can boost our partial pressure for O2 in solution any higher than what the air provides. And in the cells, we also cannot have any kind of a mismatch. All right, so the kind of exchange that's provided for dissolved gases, like in the lungs and in the cells, is what we'll see later is very different for what you have for the digestive system, where you end up taking up more nutrients in the blood than what we end up pooping out of our bodies, and in the kidneys, where we can provide a different solute concentration in the urine from what's in the blood. So those are very different exchange organs than what we see for the respiratory system. More on that later.